Okay, pretty straightforward lab. And again, this lab is optional only, just because the timing didn't work out, but I didn't want to have a lab period where we're going to do another study session. So for those who are interested, you can get a couple extra points. You can get a couple extra. I'm not giving you, right? You're getting your earnings. So just make sure you have terminology. But essentially, it's all based on doing transmission line and per unit and pi equivalent models. So you've got some impedance data right here. This wakes up at least. Oh. So you got a three-phase transmission line. You know it's 345 kV. So the very first thing we're going to do is try and draw our pi equivalent. Now with this, yes, sir. Oh, why is it not coming on? Thank you. Hit the wrong button. So if you can't recall, here is our sending end side. Here is our receiving side. This is IR. This is Z. This is Y over 2 and Y over 2, right? This is the pi equivalent for the entire length of the line, not just for a small section, but the entire length of the line. So the very first thing I would do is I would solve for my medium length line, because that's going to be okay. Here are A, B, C, D parameters. So if you remember, this is equal to 1 plus Z Y over 2. This is equal to Z. This is equal to Y over 2 times 1 plus ZY over 2. And lastly, this is going to be equal to A. Double check those because it's been a minute since I've done those equations to make sure that those are correct, but those hopefully are pretty darn close to my equivalent representation. So now I know what my ABCDs, but I need to know what Z and what Y are equal to. Those are capital Z's. This is going to be equal to lowercase z times the line length. And this is going to be equal to, not lowercase, but lowercase y times the line length as well. Be careful, right? Because these here, this is in ohms per kilometer, and this is in micro Siemens per kilometer, right? So you got to make sure that you multiply this term by J, and this term is also multiplied by J. Why is that not multiplied by negative J? Well, because X sub C is equal to 1 over 2 pi FC, and we'll call it Z of that is going to be equal to 1 over 2 pi FC times J, which means it's negative J over 2 pi FC. Now I just invert to go Y over C, and I end up with omega times C divided by negative J, which in fact equals J omega C. So all you need to do to convert those, right, is just make sure that you have the J term included in there. So this is per kilometer. Wake up. You know the line length. And you should be able to calculate uppercase Z and uppercase Y based on those parameters. Once you have uppercase Z and uppercase Y, you should be able to solve for your ABCD parameters. Now, we've got to go back to the lab handout and look, what are the load requirements? Boy, oh boy, this computer is really working hard today. So we want to go ahead and calculate the reactive power supplied by the sending end if the receiving end is maintained at 1 per unit voltage for loading conditions of 0.75 SIL and 1.5 times SIL. We should already be thinking this is written in terms of surge impedance loading, right? For the lossless line. And we said anything less than 1 per unit SIL means that the line should be supplying reactive power. Anything greater than the SIL should be absorbing reactive power. So if I look over here, the power factor should be greater than 0.9. And over here, it should be less than 0.9 because that line needs bars. In the other case, it's supplying. So 1 per unit voltage and a lagging power factor means we're good to go and actually start modeling this up. So let me clean up my model again. Now we have Z, Y over 2, Y over 2. This is VS, which is a question mark. IS is equal to a question mark. What does VR equal? Well, since my units are given in terms of ohms, I don't have any transformers. Why bother doing anything in per unit? It's just more work. So 1 per unit voltage means 345 kV. So let's make VR equal to 345 kV at an angle of 0. But don't forget, we need to make sure we convert that to a phase voltage. So we divide by square root of 3. Then we solve for IR. How do we get IR? This is P, Q, and S. That angle theta at the receiving end is equal to the inverse cosine of 0.9. What does S equal? Well, it tells you it's 0.75 times the surge impedance loading. And the surge impedance loading is V squared over Z sub C, right? The characteristic impedance for a lossless line. That's 345 kV squared divided by my characteristic impedance, which is that capital Z that you calculate once you multiply the little z by 200 kilometers. So once I have S, now I know that S, so S, and I'll just call it SIL, is equal to square root of 3 times, well, I'll just actually put the voltages in there to make it easier. 345 kV at an angle of 0 times the conjugate of IR. IR is unknown, right? So I'm solving for it. But this power factor over here is only going to give me a magnitude. I've got to go ahead and calculate that angle. That angle is the inverse cosine of 0.9. So IR is going to be equal to the S of the SIL at an angle of inverse cosine of 0.9 divided by the square root of 3 times 345 kV, all that conjugated. Right? That's the generic equation for IR as a function of my load. So I've got to now run a table, 0.75 and 1.5, and then you're going to go ahead and calculate an IR value using this formula. Once you have that, your next step is to do your pi equivalent. Because you have all the information you need, right? You've got VR and IR at this point. And once I have VS and IS, S is going to be equal to, not the square root of 3, because these are phase voltages. Okay? That's the input power into the line. And then what I'll show you is, you know, here's a point and then 1.5 with a 0.9 lagging power factor. So the question is, does the line loading result in the consumption or supplying of reactive power? If it's less than SIL, it's supplying. If it's more than the SIL, it's supplying. So you should know the answer. You should just be able to check it from there. And then it asks you a couple other questions. And that is not necessarily going to be about the lab, the actual calculations. That's just thinking about it in terms of going from there. So I will give you a hint on number 2. If the thermal line limit is 1400 amps, what is the maximum load the line can support? S equals square root of 3 times VI, right? That's the maximum load. That's an easy one. And the last one is if you put capacitors on the line and you run it higher or lower. Think about improving the power factor, which means you drop the magnitude of S, which means you should be able to push more current to it, right? For real power, unity power factor is always the best because the magnitude of the current always drops. I've got a little bit of, whoops. So again, since this is a bonus, first thing I did is exactly what we talked about, right? I went ahead and I calculated my big Z and my big Y. Then I calculated my characteristic impedance. And you can see I just entered in, omega L and V sub C. Notice I didn't actually have to include the line multiplication there because it just divides out, right? It would be 200 divided by 200, so you can cancel the 200s out of there. And then I go ahead and I calculate my SR and VR. So you can see here's the SR and the VR. And now I just do it at 0.75 at an inverse cosine of 0.9. I run through, put it through my calculator, and then I solve for VS and IS. I look at the angular difference just for some additional information, and I compare until I get to here. So let's go ahead and run right up to here. Again, you don't need to do all this extra stuff. I'm just kind of showing you how I would, oops, taking so long. All right. Well, not sure why the profile is coming up. Let's close it. Okay, so I've got magnitude difference. I've got a theta S difference, or theta S in degrees. So what do these parameters represent? Well, you can see that the magnitude difference is VS greater than or less than VR. All that tells me is I've got reactive power flow from the sending end to the receiving end, which is okay, right? That doesn't mean that I'm not getting any power from there. That just means that the line is actually supplying some bars, meaning I don't have to provide as much. And if I look at my angles between the sending end and the receiving end, here's the difference between, well, let me back up. Theta S in degrees. So that actually is the degree angle. And then here's theta R. Where's theta R? Why don't you plot? Oh, well, theta R, I think it should actually be 0, right? Because we know we specified it to be 0. So then we look at our power factor for theta R. That verifies it's 0.9. Our sending end power is here. And then we look at our Q sending end versus Q receiving. And I didn't plot those. I'll just go ahead and put QS and QR. And you notice QS and QR, 361 MVA versus 370 MVA, 270 MVA. That's a little bit different than what I would have expected. And then the Q difference is here. Oh, yeah. Okay, that makes perfect sense. So QS has 362. QR is 270. No, that doesn't make sense because the sending end should be a little bit less than that. Do I have that backwards? Let's see. I have that correct in here. Oh, and here let's check our equations first. So I said A was equal to 1 plus Z times Y over 2, which I got that one correct. B, I said was equal to Z, which is correct. I did not have C written correctly. I wrote C up over here was equal to Y over 2. So it's equal to Y times over 4. And D is equal to A. So that checks out correctly. All right, so let's keep going. So I have my sending in power, my current, and then I just display the current if you want to have it displayed. Then my sending in actual power is VR times IR, and I just denoted it running at 0.75. My sending in voltage is just in my my multiplication matrix for my sending in. Now, display VSIS. Oh, I don't know why that popped up. I didn't reassign VS. I'm not sure because the receiving end power should be greater because a line is being supported by it, unless I didn't do this correctly. That's 3 times B squared over 2. I had this divided by 3 times VR. That is correct. Let me look and type in SR. Oops. That's the absolute of SR. And then so I am dropping the power. I went from 413 to 309. So that is correct. That's V times I, yeah. It's not obvious to me unless I made a calculation mistake. Well, let's do this. Let's start. You guys can all start doing it. And while you're doing it, I will double check my work to see where the discrepancy is. I think the discrepancy is, if you notice, this is not a lossless line. So that's why it doesn't necessarily, because we only have that when it's a lossless line. If I, in fact, made that 0, I believe that the numbers would work out. Let's see if we can do that really quickly. Let me put this right after here. Run it again. Let's see if it'll clear everything. Okay, now we see the Q difference is negative, right, for the first one. So it has to be a lossless line. That's why this number doesn't work. When I include resistance, that resistance is big enough, right? The X over R ratio is only a factor of 10. We said the X over R ratio should be like 30 to 50 for it to be truly a lossless line. So when we make it 0, then we see our Q difference right here as a negative number when we have 0.75 for our SR. But when we include the resistance, we actually don't have a lossless line, especially for such a low value. So you can go ahead and do that. So just double check to make sure you're seeing these results. But so for this problem, since this is not a lossless line, you actually still have to inject bars into the system. And that's because the X over R ratio is so small. Okay, it's only a factor of 10. So yes, it does work perfectly fine for us. So I'm sorry about that. All right, any questions? Okay, I'll pause the video. What part do you want me to leave up? You want me to leave up the chicken scratches that I had here? Zoom out a little bit. Wish I could move this out of the way. Guess I can't. To start your work, or do you want to leave some of the MATLAB stuff up? It's up to you. Leave this up? Okay. All right, I will pause the video, and if you have questions, feel free to ask. Pausing, where's the pause? Whoops. So this equation here is not Z sub C, it is actually just, well, it's Z of the capacitor. So I'll put capacitor here. The equation for a characteristic impedance is the square root of L over C. All right, or in this case, you could also do this, omega L over omega C, because the omegas will divide out. So sorry about not showing you the correct ZC here. So the characteristic impedance that you use to get SIL, where is the equation? It's right, this equation, that goes there. So it's a different ZC, sorry about that.